Hi, I'm Paul Kyogan from GKTuition, and in this video I want to talk to you about geometry. Now the question I've chosen to go through here is 2017 Paper 2 Question 5 Part A. We're given a rectangle and we're given a number of lengths and there's a few triangles within our rectangle. And in the first part of the question we're asked to prove that the triangle AFE and the triangle DAE are similar, or in other words equiangular. Similar triangles are triangles where all the angles are the same. And in order to prove that two triangles are similar, you have to prove they have at least two angles in common. Because if you can prove they have two angles in common, then the third set of angles have to be the same, because the three angles in a triangle will always add up to 180 degrees. So once two of them are the same, the third one has to be the same. Now, I can't directly prove that the triangle AFE and the triangle DAE are similar. But what I'm going to do is I'm going to do this in two different parts. First of all, I'm going to prove that the triangle AFE and the triangle DAF are similar. Then I'm going to prove that the triangle DAE and DAF are also similar. If this triangle is similar to that one, and then DAE is also similar to that one, then the two triangles AFE and DAE must be similar to each other. So as you can see, I've done the first one out here. I find it very useful to change the orientation of the triangle, so I'd always sketch a triangle like this. It's a lot easier to visualize here. This is my AEF and this is my DAF. I need to prove they have two angles in common. And every time I do it, I have to justify it. So I started off with AFE, which is the angle here, is equal to the angle DAF, which is the angle here. Clearly they're both to 90-degree angles, so my explanation is that they're both 90 degrees. I also can say that the angle AFE and the angle DFA are the same because they're a common angle. If you look at your triangle, that angle there and that angle there are the same thing, so it's just a common angle. Once I've proven they have two angles in common, I can conclude that the triangle AFE and the triangle DAF are similar. Next part of the question, I'm going to prove that the triangle DAE and the triangle DAF are similar. The second part of this is almost identical to the first part. Notice again, I've drawn my two triangles beside each other and they're in the same orientation. I have the triangle DEA and the triangle DAF. In this case, I've said that the angle DEA, which is this one, is equal to the angle DAF, which is this one, because they're both 90. I can say that the angle EDA is equal to the angle ADF, because they're a common angle. If you look at the larger diagram, that angle there and that angle there are the same thing. So it's a common angle. So I can conclude, once they have two angles that are the same, I can conclude that the triangle DEA and the triangle DAF are similar. But in the first part, I proved that AFE and this one are similar. So if AFE and DAE are both similar to DAF, that means they all three of them have the three same angles. That means that the triangle AFE and the triangle DAE are similar. And that's what we were asked to prove at the start of the question. Okay, the next part of the question asks me to find the value of AD. So in this case, I've drawn my diagram from part A. I proved that the triangle AEF and the triangle DAF were similar. If they're similar, that means that their sides are proportional to each other. The one opposite the right angle is proportional to the one opposite the right angle. The one opposite the angle F on this one is proportional to the one opposite the angle F on this one. The base of this one is proportional to the base of that one. In other words, the hypotenuse of the one on the left over the hypotenuse of the one on the right is equal to the side of the one on the left over the side of the one on the right, which is equal to the base of the one on the left over the base of the one on the right. The question was to find the value of AD. Now at the moment I don't have enough information there, but I can work out another value. If you look at the triangle AFE, that's a 5 and that's a 12. So I can use Pythagoras Theorem in this case to work out my hypotenuse. If I use Pythagoras Theorem, my hypotenuse works out as 13. So I know the hypotenuse here is 13 centimeters. But if you look at your two triangles, the hypotenuse of this triangle is AF, the base of this triangle is AF. So that one must also be 13. The question is to find AD. So I'm looking for the side of this one, which means I'm definitely using this, I definitely need to use this fraction. The fraction, the side of the one on the left over the side of the one on the right. And AF over DF at the moment is no good to me because I don't know what DF is. So I don't need to use this fraction at all. I'm going to use EF over AF because I know that EF is 5 and AF is 13. So if I sub in here, my only unknown is AD. So if I just sub in here, my AE in this case is, my AE is 12 over AD, which is my unknown. That's equal to EF, which is 5, over AF, which is 13. All of a sudden I've got one equation, one unknown, I can find the value of AD. So in this case, you can just multiply both sides by 13 AD. 12 multiplied by 13 is 156. 5 multiplied by AD gives me 5 AD. And if I just now divide both sides by 5, I'll get AD, the length of AD is 156 divided by 5. And if I plug that into my calculator, I get 31.2 centimeters. So AD in that case works out as 31.2 centimeters. Okay, part C here is largely the same as part B. I've been told that the triangle AEF and the triangle ABG are similar. So you should set up your orientation so that you can visualize what's going on. I know this is 13, this is 12, and this is 5. And the distance, if you look at your large diagram there, the distance from A to G is clearly 12 plus 27, which gives me 39. If these triangles are similar, then clearly the hypotenuse of the one on the left, AF, over the hypotenuse of the one on the right, AG, is equal to the side of the one on the left, AE, over the side of the one on the right, AB. And the question is to find the value of AB. So if we just sub in here, we know all the other values, so we'll be able to find AB. AF, in this case, the hypotenuse of the one on the left is 13 over 39 is equal to the side of the one on the left, 12 over the unknown that I'm trying to find, which is AB. Now if I just multiply both sides by 39AB, I'm going to get 13 times AB is equal to 39 by 12 is 468. Now, to get AB on its own, I just divide both sides by 13. So my final answer here is just AB is equal to 36 centimeters. So A is equal to 36 centimeters. The final part of this question requires us to find the area of the quadrilateral GCDE. A quadrilateral just refers to any random shape that has 4 corners. So obviously this is an obscure shape, and in order to work out the area of GCDE, now look at your large diagram as I described this. Look at the diagram in the exam papers. It's the area of the triangle ABCD, so the whole thing minus the triangle ADF. So minus the large triangle ADF, and then also minus the large triangle ABG. So I subtract the 2 large triangles, but the issue there is I'm after subtracting the small one in the corner AFE twice. So I actually then have to add on the triangle AFE. So the whole rectangle minus ADF minus ABG plus AFE will leave me with GCDE, the area of the random quadrilateral shape. Okay, so I've done out all my diagrams here, and you'll notice I've got my 3 triangles in the same orientation. In order to get the area of a rectangle, it's just length by width, so no issue here. It's just 31.2 multiplied by 36. In order to get the area of a triangle, so I'm going to subtract now the area of ADF. The area of a triangle is half the base by the perpendicular height. So in this case, it's just a half multiplied by 13 multiplied by 31.2. I also need to subtract the triangle ABG. But the issue here is that I don't actually know what the distance BG is yet. We haven't actually worked it out. If you look at the triangle ABG, you worked out that AB is 36, and from the diagram, AG is 39. If you know 2 sides in a right angle triangle, you can use Pythagoras to find the other one. If you use Pythagoras Theorem in this case, you're going to get 15. The side BG is equal to 15. And that allows me to work out the area of the triangle ABG. It's just half the base by the perpendicular height. So I'm going to subtract again. It's a half multiplied by the base, which is 15, multiplied by the perpendicular height, which is 36. The final thing I need to do is then add on this smaller triangle because I'm after subtracting it twice. So to add on the area of this triangle, again, it's half the base by the perpendicular height. So it's plus this time a half multiplied by 5 multiplied by 12. So it's the area of the large triangle minus ADF minus ABG plus AFE. Sorry, that's a rectangle. You plug all that into your calculator, and your final answer there is 680.4 centimeters squared. So when you're dealing with area, remember things are always going to be squared. Now, I hope this video made sense. I think in general, Leaving Certs tend to struggle with that. They just don't get enough time to revise over that kind of thing. If you've any issues with that at all, then as always, just ask me in class or send me an email and I'll try and clarify for you.